Well, hello everybody. We're going to talk today a little about something that is, everywhere right now, and that is social distancing and whether or not that's effective, right? Because we kind of think about it, a lot of people right now are a little bit frustrated or maybe feeling a little like cabin fever, like, oh, I want to get going, or, you just kind of want to see other people a lot of times. Um, and so, like, our thought is, is all of this isolation and all of this, closing schools and everything else, is that an effective measure to kind of slow the spread of COVID 19? Does that actually work? So that's what we're going to be looking at today is the math behind, social distancing. And does that stuff actually work? So what I'm going to do is just kind of, these aren't actual numbers for the virus itself. We're just going to kind of, use this so we have a jumping on point for learning a little bit of math behind this here. So stuff that I'm just taking off here is that maybe something infects 3 people every 5 days. That's kind of the information that we're going to start with, which I think is kind of a little bit higher number than what necessarily COVID 19 does. From what I've heard, it goes anywhere from about 2 to 3 people every 5 days. So I've decided to kind of take the higher value here. So a few things go on when we kind of try to think about this, and we, I mean humans, right? Humans are not great mathematical thinkers just right away. We kind of have to go ahead and work it out to see, uh, does it actually work, right? We're not great at intuiting a lot of mathematics because here, even myself included, when I think about this, I think, okay, hey, if 3 people are getting infected every day, that does not sound like a big number to me. That sounds like, okay, well, after 5 days, there's 3 people, and then, after 10 days, maybe there's 6 people, and then there's 3 more every 5 days. That's not so bad. After 30 days, there's only like 18 people, maybe, if I just keep 3 and 6 and 9 and 12. And that's how a lot of us think. But the problem is that we're thinking about things in a linear fashion. That's what humans are actually pretty good at, is thinking about things in a linear fashion. But when we have to think about things that are non-linear, that's when they get a little bit difficult to kind of just intuit. So here, that has a few problems with it. So what we're going to do is just kind of look at how does that go. We'll get a visual going here. So let's say here we have the number of days that have been going on, and then we could say the we'll just say the number of infected people. So we're just going to put that down on here, and so we'd have to start with like somebody, right? Somebody, gets sick or whatever. So we'll call that on day zero, one person gets infected. And so, like, that's, fairly common. And so for that, I'm just going to put a little circle here to represent there's one person who got infected with something. And now, kind of our intuition would say, well, if we follow this pattern after 5 days, 3 people will get infected. And so this is where kind of problem number one creeps up in our thinking, where we might go 5 days later, myself included sometimes, I think, gosh, 3 people will be infected, but that's wrong. What we should really say is that 3 more people will be infected every 5 days. So it's not one here, we're actually going to go up to 4 total people because 3 more people will be infected. And to kind of see how that works, right? If I've got one person here, and I kind of spread out, this person is going to infect 3 more people. And so there are now a total of 4 people on our infection web. So it's already a little bit more than we would have expected. Not that much, 3 versus 4, not too bad. But now we're going to move out to the next spot, right? After 10 days, how many people will be infected? So I'll let you kind of think about that first. I want you to get a guess down there. Maybe you already know. And so in here, I'm just going to work it out and see what we actually get. So each one of these spots infects 3 more people. So this one infects 3 more. Put that one on there. This guy here affects 3 more also. One out here infects 3 more people as well. And even the guy in the middle, this person also spreads out to 3 more people, right? And so already our web is starting to look pretty entangled, right? We're pushing all this stuff out there. Now in this case, you could go through and count every single one. I was kind of counting them in my head as I put them up there. There are 16 total infected people in here. Maybe you can start to see what's the pattern that's going on in here. And so we could keep pushing this pattern out, right? What's going to happen after 15 people, right? So take your guess there. I'm actually going to go ahead and draw all these up here to make sure we can see how that's going to go. I'm going to choose a slightly different color so I can keep track, because it's going to be quite a few of them. But you can go ahead and take your guess on there, and if you really want to, just jump forward in the video and see if you're right. So each one of these has to have 3 people on it. So I'm going to put 3 people. I just have to double check. I think that's everybody on there. So now our web has gotten really, really huge. And you can go through, you can zoom in, maybe take a count on each one of those there. This is now up to 64 people that would be on here. So if you took that as your guess, you can kind of see what the pattern is. It's multiplying by 4 each time, which that leads to kind of another misconception that would happen a lot, is that if somebody's infecting 3 people every day, even if we get past the linear misconception and we think, yeah, we'll need to multiply, so we would multiply by 3 each time, but in actuality, we also miss out that, hey, that first person also counts, and so it's not times 3, it's times 4, because that one extra person counts in there. So if they're infecting 3 people a day, we multiply by 4. If somebody was infecting 5 people every so often, we'd have to multiply by 6. You always have to multiply by 1 more than whatever the number of infection rate is, because that's how that's spreading. Every single person is spreading again. Now this is an oversimplified model because there's obviously lots of different things that could happen, but in this simplification, right, that's how we have to think about that, right? And so we can kind of look at, what if we wanted to push this out even farther, right? What if we wanted to look a month ahead? How many people are, how is this going to be affecting? How many people are going to be infected? Well, here we can kind of look at the pattern that's going on here. Some of you guys maybe have thought about that already, but we've started with 1 person, right? So if I put that up here, we started with 1 person to start, and then we took that 1 middle person and took that times 4. That was that little central piece that we had there. So that's times 4, right? That was to get to this first iteration, right? What's called an iteration every time something's happening. So the first iteration was just times 4. To get to the next iteration, we'd go times 4 yet again, right? That would be to get to here. And then to get to the next iteration, we go times 4 again, right? Which would just make sense. We're repeatedly multiplying, right? And as you guys know, repeated multiplication can be represented with exponents. We can just say this is 4 to the 3rd because we've done 1, 2, 3 iterations, right? And 4 to the 3rd, you check it in a calculator, is 64. That's what that thing gets. And so here, if you're listening to the news or anything like that, they'll often say that this virus grows at an exponential rate. And the reason they use the word exponential is because we're repeatedly multiplying every day to get the new amount of infected people, right? Or at least to estimate that, right? So in here, we could also push this out. We could say, hey, I wonder how many people are going to be infected after 30 days. If we kind of jumped ahead there, how many people would be after 30 days? Well, I'd have to think, how many iterations that would take. We're going every 5 days, so 30 divided by 5, that would give us 6 iterations We'd multiply by 4 6 times, meaning we'd need to go 4 to the 6th power. So that's where I would grab my calculator, because I do not have that memorized off the top of my head. And I would just type in 4 to the 6th and find out, oh, 4,096 people would be infected in just 1 month, right? So 4 to the 6th being 40,096. That's a lot of people after just 1 month. And that just came from one person, without any social isolation, without any social distancing, without any of that stuff that we're doing right now. It grows rather quick. And I'm not going to draw all those because that would take a really, really long time. It already took me long enough just to get to here. The next iteration past this, every single one, it would just keep spreading and going and going and going, getting larger and larger and larger. So in here, how do we make this slow down? How do we not have it get as high quite as quick? Well, there's a couple of different ways we can do that. Number one is to change what's this first multiplier, right? If we make that first number a little bit smaller, then the whole thing gets a little bit smaller. But that's pretty tough to change. We can't go less than one person. In fact, it's probably going to be more than one person that we would start with. So that one's not really changeable. So the only thing that's happening in this equation is multiplying by this same number over and over. So we can only really change this number here, right? We can only change the number of people we infect every so often, right? That's the only thing that we can really limit, and that's why we do social distancing. If we can reduce this number down a little bit, we can maybe prevent and have less people become infected overall. And so that's your guys' task. I've uploaded a document onto Google Docs. It'll look something like this, right? There's a little bit more to it than what I have just up here on the board, but it's kind of the same thing, right? If we kind of play around with the infection rate, or kind of play around with how fast things are going. So like on here, somewhere, like I said at the beginning, between 2 to 3 people get infected every so often. So I just took the average of that and said, well, let's say 2.5 people get infected every 5 days, right? How many are going to be there after 30 days? Kind of the same thing that I did over there, right? Using an exponent to figure that one out. And then we can go ahead and say, well, what if we do some social distancing, right? How is that going to work? If you kind of distance yourself away from people and come in contact with 50% less people, or you cut your amount of contact in half, we would be able to take this number, cut it in half first, and then use the exponent to figure that out, right? So in here, well, I wonder what that would do, right? How's that going to change that final number, right? Hopefully it reduces it, but by how much? Is it just going to cut it in half? Or is it going to cut it in more than half, right? Or less than half? Is it not effective at all? And then also checking, what if we did 75% isolation? So you remove 75% of this stuff, or maybe you think on the flip side, what percent is left? And then in your assignment, I also put down, what if we did 90% isolation? So you have only a certain percentage left over, and then how many will be left after 30 days. And so that's your assignment for today, is to kind of figure out, based on this base amount, how does that effect in the social distancing actually work? And I took some of it and changed the infection rate just a little bit on there. Yours, you can fill that out on the Google Docs and then send that in to me. Thanks.